everyone, this is Professor Iris Miano. I have your Day 16 lecture here, finally introducing you to trigonometry in this class. So before we get into too much depth, eventually we'll be talking about unit circle. We need to discuss fundamental elements of the unit circle, which include the most basic things, angle measures, and also what types of materials make up an angle. And that's where we see our very first figure here introducing a ray, which they call a half line. If you have some geometry background, a ray is technically defined as a line on one half of the side. I guess you could just call it a half line. Sure. I used to define it as what would happen if a line segment in a line had a baby, because the line segment, as you know, is a some fixed length straight line trajectory with endpoints, and then a line goes on forever in both of the directions in which it points. So if they came together, it'd be a line on one side, a line segment on the other, and they would name their baby Ray. LOL. Okay, anyway, so if you have two rays coming together such that they are sharing their endpoint, then the amount of swing that it gets from the initial side to the terminal side is, where the angle lies in there. Although you can go beyond the terminal side and swing around a full revolution plus some. That's what you see in the part C of figure 2. You could also swing on the clockwise direction, which is non-conventional. That's associated with negative angles, as you can see here. Counterclockwise is the quintessential direction associated with positive angles. So as you can see, the vertex is illustrated here in figure 2, parts A, B, and C, and that's the connection of the two rays. One of the rays is the initial side, the other one's the terminal side. So the initial side is pretty much always this horizontal ray, and you'll see this again in coordinate planes like you see here in figure 3. The standard position of your initial side is going to have the vertex positioned in the origin, and then a positive angle is going to be a counterclockwise swing from the initial side, which is a horizontal ray, matched up with the positive part of the x-axis. And the terminal side could be anywhere in the coordinate plane, and the swing of the angle that gets you from the initial side to the terminal side is the angle measure theta. And if you have a counterclockwise swing, or a clockwise swing, when you have a clockwise swing associated with your angle measure to get from the initial side to the terminal side, then the angle is negative, as you can see here. Okay, so what is next? Yes, depending on where your terminal side lies, that'll determine the quadrant in which it exists, and in the quadrant in which the angle exists, or where it lies. So this is an example of a quadrant 2 theta or angle measurement. Here's a quadrant 4, here's a quadrant 3, and if we had a terminal side somewhere in this region right here, that would be a quadrant 1 angle. And also if the terminal side lies, on an axis, then it's a quadrantal angle, which is kind of hard to say. So there you go, have fun with that. So there are some very famous angles that come up, like they're just super duper basic, and that'll be associated with what we call a full revolution, or 100% of a swing, so to speak. Would be associated with 360 degrees. This is where numbers are going to start to come into play here. We're going to have degree measurements associated with angles, and also a new type of measurement is going to be introduced. I'll get to that in a minute. I'm not going to spoil it just now. For now, let's just talk about these famous degree angle measurements. So going 360 degrees is making a full revolution about the vertex, If you want to make a quarter of a revolution, that's equivalent to 90 degrees or a right angle. Notice the placement of this little box inside of the angle area. Also, even though this looks like a line right here, it's actually two rays joined at this vertex, and it is forming a 180 degree angle or half a revolution. Okay, great. Some more examples of angles presented in coordinate plane. Here's a 45 degree angle, which is halfway of a swing from the x-axis right here to the y-axis in the first quadrant. If you wanted to have your swing go negative, you would just have that terminal side move from the initial side in a clockwise manner, whereas the positive angles are always moving in a counterclockwise manner. Also, you could have a swing going up beyond 180 degrees, in which case it would be lying either in quadrant 3 or 4. Here, this terminal side happens to be in quadrant 3, and it's representing a 225 degree angle. And then also you could, believe it or not, have an angle swing that's more than 360 degrees. And whenever that happens, it's going to be a full revolution plus some. So if you want to know where that terminal side lies, essentially you just subtract by multiples of 360 degrees depending on how high this degree measurement is. 304 is only, more than one multiple of 360 degrees, so simply doing the subtraction there would give you the equivalent degree measurement there. So that'll be a 45 degree angle would be equivalent to a 405 degree angle. Do you guys see that there? And hopefully the visual is very striking comparing figure 6 to figure 9. You can see that the blue terminal side lines up between those two. So we can say that those angle measures are equivalent as far as their end result is concerned. Now, so 360 degrees, yes. So angle measures are, when they're in degrees, they are broken up into those 360 pieces, but you could break them up into smaller pieces. And herein lies this conversion, a little box here, this yellow box, in which we can break a single degree up into 60 more pieces, and those are called minutes. And then each minute can be broken up into 60 smaller pieces than that, and those are called seconds. Okay, so there you go. So let's have some practice in which we use these conversions in order to take this degrees, minutes, seconds into this measurement into just an angle that's just in degrees but with a decimal. Okay, so how would that all go down? Well, I'm pleased to show you. Let's have my drawer in place, and we'll go purple with it to begin with. Sure. So you want to take this minutes number, the 42, which has the one tick mark on it, and you want to basically divide that by 60 in order to give yourself the degree measurement associated with the minutes. So therefore, this is 42 over 60. Right, because 1 degree, so this is giving you the percentage of 1 degree that is represented here by the minutes, okay, which is 0.7. And then here, for the 21, if you want to divide this into decimals, you not only have to divide it by 60, to turn it from seconds into minutes, but you also have to divide it by 60 again to turn it from minutes into degrees. So basically, it's like you're taking this 21 and you're dividing it by 60 times 60. It's like you're dividing it by 60 twice over, which is 300 or 3,600. There are other ways to think about this conversion process. You could think about it more in terms of a unit conversion, and we can talk about that more in class if you would prefer a different take on this. But reaching for your calculator here, because why not? we will get 0.0058, and then 3's forever. So I'm going to put a little vinculum on top of that 3, which is what the bar on top is technically called. So this is the decimal that you tack onto your 61 degrees, accounting for the minutes, and this is the decimal accounting for the seconds. You have to add them both together and then tack them onto the 61, and that'll give you your final answer here. So 61, oops, excuse me, hold on, let's erase that. 61.7, and then there's 2 zeros here, so the 7 will go here if you add it together. Then it's 0.583 with a vinculum. Oh, but wait, we're going to round to 2 decimal places, so how does that go down? Well, you want to check in with the second decimal place that you're rounding to, and then also look at that neighbor. That neighbor is a 5, so that's going to bump that 0 up to a 1. So your final answer that you should be boxing up here is 61.71, and then don't forget that the units are in degrees. Okay, and that'll be that for that one. Okay, so remember, the rule of thumb is this: if you want to take your measurement that's in degrees with minutes and seconds, you take the minutes, divide it by 60 to get that decimal representation. You get the seconds and divide it by 3,600 to get that decimal. Add them together to the 61 or whatever the degree measurement is out in front, and then you get the entire degree measurement in its decimal form. Okay, now let's go the other way with it. And how would you do that? Yikes. So again, we are given something in degrees with a decimal, and we want to go into degrees, minutes, seconds form. And we're going to round our answer to the nearest second. So here we go. Take that 40, oh, excuse me. Yes, let's take that, this time I'm going to set it up as a proportion because I think it's a little bit easier to see it this way. So I'm going to make, actually, hold on, let me erase that, the right utensil out. I'm going to have some blank space where I want it to be minutes, right? I want to figure out what the minutes are, and if I divide that minutes by 60, I should get, just take the entire decimal here, folks, which is the 0.411. And you may be thinking, well, why do I take the whole thing? Isn't some of it just going to be associated with the seconds? Yes, but you're going to deal with that in another step, okay? So let's go ahead and just a moment. Hold on, let me check something with my calculation here. I'm going to push pause. Okay, I'm back. Sorry, there was just something a little bit unclear in my notes, but I got it down. All right, so the ratio is this. Here, I'm going to have my minutes, whatever goes in this position. Well, at least the whole number part. The decimal part, I'm actually going to use that in order to find my seconds. Whole number part. Okay, so, and the way it works is you have your minutes here, you divide it by 60, and that's supposed to be associated with the decimal, and you want to put that over a 1 so that, you know, your proportion makes sense. So basically you do the cross product here, and you're going to find that the number that goes in this position, I'll go ahead and do it in this other color, is 24.66. Okay, so the 24 is going to be your minutes. Or actually, hold on, let me do this a little bit more of a slicker way. Watch this. The 24 goes here, and the 0.66 is going to be transferring over to this other proportion that you're going to set up. Again, so you'll have some box, and it's going to be divided by 60 one more time, but in this position here, you're going to have the decimal from the minutes calculation over a 1 again. Okay, and then you're going to do the cross product again, and then this is going to give you your seconds. And whatever this value is, you're going to round it to the nearest whole number. So I'll put a little note there, round to nearest whole number. Okay, cool. So what do you get? You take the cross product and you shall get 39.6 if I'm not mistaken. 39.6, but again, round, and that'll give you 40 seconds. So it's 40 seconds. And it was 24 minutes here. Okay, so now we're ready to convert this all down here. Remember, this the whole degree measurement stays the same. You're just going to be performing a couple of manipulations on the decimal, and you'll take it in parts like this. Okay, so just to be clear, the final answer here is 29 degrees, 24 minutes, and 40 seconds. Cool. So this will work. I think it's a little bit more difficult to go from the decimal degree measurement to degrees, minutes, seconds, but as long as you take the pieces and put them in their correct places in this process, you'll be fine. Okay, cool. So hopefully that was fun. Great. Let's go ahead and now finally, formally introduce what a radian is. So a radian is a special angle measurement that has been introduced at this juncture so that we have a mechanism for thinking about these angle measurements in a way that doesn't have any units or dimension. And we do that so that certain calculations that come up later in various applications make sense in terms of the units, okay? We could go into more detail on that later or not. It's up to you. Hold on, let me just press pause real quick. Okay, I'm back. Sorry, my daughter came in for a quick visit. Where were we? We're talking about radians. And so basically, the radian comes about by relating how, like one whole radian is going to be the measurement of this angle right here when the radius is equal to the arc length that is made by the central angle that is formed right here. Okay, so when the central angle gives you an arc length equal to the radius, that central angle is 1 radian in measure. Okay, so hopefully that makes sense. And here is a formula relating this radian theta measure. So theta is a Greek letter that represents degree measurements, or excuse me, angle measurements either in radians or degrees. It just needs to be specified. So it doesn't matter if it's, you can use the symbol theta. All I'm saying is that it could be used for radian measurements of angles or degree measurements of angles, not to make things even more confusing. So arc length is going to be S, radius is R, and when they're equal to each other, we have, 1 radian being represented there. Okay, great. So please also note that these radian measures are proportional to arc length. Okay, so that's what this little figure and also proportion is representing. And then we're presented with various conversion facts right here, which are going to help us go from degrees and radians and back again all day long, and to also think about these things in terms of revolutions, swings around unit circle. Okay, so if you want one complete revolution, it's the same as a 2 pi radians in movement, which is the same as 360 degrees. Now, if your radius is something other than 1, then we need to talk about what's going on with various measures that could be going on here. We'll talk about that in 5.2. It's coming. Okay, and here is a nice table showing all of the different common angles and their radian counterparts, just for easy reference. So this is something that we could come back to later. You can flip back and forth to it if you find that it's conducive to some of the examples we're going to go over in the rest of this section. And also your homework, having these things readily available to you, referencing them as you practice, I think is the best thing you can possibly do. Looking at it over and over again is great. It's going to help you internalize this information. You're going to start to see patterns, and it's all going to become part of your heart and soul if you let it and if you give yourself enough practice. So let's go ahead and entertain some examples here. And of course, I get these straight from your book, so they're exactly like homework problems that you're going to be encountering as well, which also, come from the same author. So we're going to tackle number 36 here, which is asking us to convert the angle from degrees to radians. Okay, now remember, if we're going from degrees to radians, we should use the conversion of, what was it? Hold on, let me flip back just to reference it here. Well, so you could use the fact that 2 pi is the same as 360 degrees. That's what I often use. Or you could use pi is the same as 180 degrees. Personally, I've been, ingrained to use this conversion ratio, 2 pi over 360 degrees. It is okay to use pi over 180. In fact, that's not how I have it in my notes because this is just my go-to. And also you could do this thing where you put this over a 1. And why do I want to use this ratio? Well, I want to cancel out the degrees and be left with radians, which is unitless technically, right? And so you'll need to come up with a unit rate that has the same units in the opposite direction or in the opposite position as the original number. So the original number 120 degrees is in a numerator space, so I need to come up with a unit ratio that has degrees in the denominator space so that the degrees indeed cancel. Boom, boom. And then also the zeros here will cancel. Yep. And then how many times does 12 go into 36? Well, 12 goes into itself once. It goes into 36 4 times, right? And then, or 3 times, excuse me. LOL, JK, it's 3 times. Ooh, good thing I caught that sooner rather than later. All right, so what's left? Well, a bunch of factors of 1, no units, and there's a 2 and a pi in the numerator space, a 3 in the denominator space. So that'll be 2 pi over 3. Certainly, though, we could just go up to the chart, right? 120 degrees is on there, and we could just say, oh, it's 2 pi over 3. But if you didn't have the chart handy dandy, you can use one of these unit ratios. You can come up with a similar unit ratio. This, again, this 2 pi over 360 degrees or vice versa, whatever's more appropriate to you, that got just hammered into my head. Just for the sake of argument, though, pi over 180 or 180 degrees over pi is certainly appropriate as well. I'll go ahead and use that for this next one here. So here's my unit conversion. Pi is equivalent to 180 degrees. So that's going to be my unit ratio. I'll put that negative pi over a 1. And notice that happily these pi's cancel out. Boop, boop, right? I have units to take into account, and I have a sign that I need to recognize is still very much in play. So that'll give me negative 180 degrees. Yes, you can have a negative angle measure, and that's just going to be representing a clockwise swing in your coordinate plane as far as the conceptual visual is concerned. Okay, great. Moving on. Now, let's go ahead and calculate some arc length. So we're going to take into account this arc length formula that was given to us. Okay, but remember that theta is in the formula is in radians. So we're going to have to take this 120 degrees that's given to us in order to calculate the S, which is our arc length, in fact. Yeah, the length of the arc. Okay, great. So again, let me just start from the beginning and read the prompt in its entirety. The length of the arc of a circle of radius r, subtended by the central angle theta, is denoted by s. Find the missing quantity. Round your answer to 3 decimal places. Okay, so r equals 3 meters. The angle in question is 120 degrees, and we're trying to find s, right? Okay, now 120 degrees. Let's do a quick conversion of that in order to get at, using this formula. The formula in question, again, is S equals R times theta, right? But remember, theta is in radians. So what's 120 degrees in radians? Well, it's 2 pi over 3. We did that one already, right? Sounds familiar. Okay, so now we can use this formula as being S equals R was found to be 3. And we're going to multiply that by 2 pi over 3. And the units here are 3 what? Meters, right? So it's cool that we have this unitless measure in the angle theta, so that when we multiply it by this meters value, we're going to get meters popping back out again, which is exactly what we want for the arc length, because the arc length is a distance. We don't want to gum up the works with the idea of throwing in a unit of degrees. It's not going to make sense for us. So we're very happy. Those cancel out, and we're left with 2 pi meters, which feels weird, right? But it's just some distance, and pi is just some number. So S, the arc length, will equal 2 pi meters. But wait, they asked for 3 decimal places, so you actually need to plug this into your calculator, and you're going to get that it's approximately 6.928 meters. Or excuse me, 6.283. My bad. I was looking at a different problem in my notes. Just a moment, sorry, 6.283. That is indeed the meters arc length, and yes, it is approximate. We are rounding to 3 decimal places, so there you have it. Okay, now whenever we talk about arc length, which is, a portion of the circumference of an entire circle, it's usually follows that we talk about the area of a sector, which is the area of some portion of that circle. And we can do so now in terms of this radian theta measure of the central angle associated with the sector. Okay. So here's the formula, which is, different than what you're used to when you're talking about theta in terms of degrees. We need to be very careful that we understand that theta here is in radians, not degrees. Okay, and that's what makes this formula work. So, yeah, and I have a note that if you want to know how this formula is derived, of course, check out what your textbook has. For our purposes, I'm skipping over that and just focusing more on showing you how to perform calculations with this. So we have a similar problem like we did with the previous number 78. Is we are going to be tasked with finding the radius of a certain particular circle that has a sector area of 6 square centimeters and a central angle of 1/4 of a radian. So it's basically plug and chug, folks. What do? We need to just put in 1/4 for theta. Oh, and here's the formula. Let's reference the formula. It's A equals 1/2 r squared theta, where r is going to be the unknown that we're solving for, a is a 6, and theta is a 1/4. So it is literally just plug and chug. All right, plug and chug. Here we go. So it'll be a 6 right here, a 1/2 r squared times 1/4. Okay, so let me make that r a little bit more aesthetically pleasing. Much better. Okay, so notice that we have this r squared is technically in a numerator space. If it behooves us, go ahead and throw that over a 1. So it's abundantly clear that there's an entire factor of, well, 2 times 4 in the denominator space, 8, that we want to get rid of in order to move forward towards solving for r, because that's our unknown. Okay, so I'm going to multiply both sides by 8. So this 8 is going to cancel with, hopefully everyone's okay with this algebraically, the 2 and the 4 are going to cancel out with this 8, and I'll be left with just r squared on this side, and it'll be equal to 48. So now we have to take the square root of both sides, and I know what you might be thinking algebraically, we got to do the plus minus, but remember we're talking about a radius which has it's a distance, so we're not even going to bother with thinking about this whole like plus minus business. We're going to let the square root and the square root cancel and be left with r, and we're going to simplify just the principal square root here, okay? So that means r is equal to 4 square root 3, and it is in centimeters. Oh, but wait, they want us to round to 3 decimal places, so plug that into your calculator, and you should get that it's about 6.928 centimeters. Okay, cool. So when you're given this type of a problem, and let's say your theta was the unknown, like you have a similar problem here you're trying to find, just recognize that the number that you're going to pop out there is going to be it's not going to be in terms of pi, it's going to be the number of radians that you have here. So just be careful when you're solving for theta, okay? Cool, cool, cool. All right, moving right along. So now we're ready to entertain a very mild application, just something that has to do with linear speed and angular speed. And this is associated with the speed at which an object moves around a circle, okay? Its linear speed will be the constant speed such that it has this travel distance of s, which is the arc length, basically, and it does so over some time t, okay? The angular speed is part of that calculation, so depending on like what you're using here, if you have the arc length in question, then you can just divide it by t, and that gives you the angular speed. But if you don't have that, if you're just given, for instance, the angle in radians, that's your theta, and the time, well, then you need the what's it called? The angular speed omega, which is another Greek letter, and you've got to multiply that by your radius, and then that can give you the linear speed. Okay, so it's like depending on what you're given, you'll either calculate the linear speed this way or this way. And if you need to do it this way, this r times omega, then you need these other bits of information as well. Okay, cool. So let's entertain another example. This one is going to be that's the last one in this section, in which we are going to calculate the linear speed of passengers on a centrifugal force ride. It says similar to the gravitron. Did you guys ever ride the gravitron at, like, you know, local fairs where you grew up? Personally, I did. It was one of my favorite rides at the time when I was much, much younger. And now that I'm older, I have such an aversion to being spun around or heights. Oh, all of those things just freak me out so much. I could not handle even a second on the gravitron these days. In any event, let's go ahead and figure out the linear speed for passengers. And I'd much rather do that than go on the gravitron these days, like times 1,000. Okay, so we are given the speed, which is 22 revolutions per minute. Okay, so that's going to be relevant for us as far as being able to, we're going to need to convert it actually a couple of times over. So that's something that we'll need to do early on. We are given the radius, believe it or not. It says the diameter is 13 meters. So you take that, are these both the same color? That's so funny. You take that 13 meter diameter, and you cut it in half and you recognize that the radius is 6.5 meters, right? Because as we know from our geometry days, the radius is always half the diameter in a circle. Furthermore, what else are we given? Well, not much else that we can use without doing a couple of iterations of conversions. So let's take this 22 revolutions per 1 minute, okay? And let's recognize that we need to do some conversions in order to get radians per hour, ultimately. We need, that's what we need, we need our angle measurement to be in radians per hour, so we can multiply it by the radius, and that'll be your omega, will be your angle, your omega is your radians over the amount of time, and we want the amount of time to be converted into hours. Notice that it's initially in minutes, so there's going to be a time conversion that needs to happen. So I'm going to have to consider that in regard to manipulating this 22 revolutions per minute. So the first thing I'm going to do is turn revolutions into radians. Okay, I know that 1 revolution is equivalent to 2 pi radians, right? Now I'll put radians here, but notice that radians do not actually have units, so it's just a factor of 2 pi here. But what's cool is that the revolutions cancel out now. Okay, so now I'll multiply 22 times 2 times pi, and that's the number of radians. But wait, I need to convert these minutes into hours, right? So I need one more unit conversion to happen. I need 60 minutes to go into the mix, and note in this unit ratio that it's equivalent to 1 hour. Now those minutes are going to cancel, and I'll have radians over the number of hours. So basically what I've calculated here is my omega, which I like to do as a W but with an extra little curly bit inside. Okay, and so we'll actually multiply all of that, and you'll get what? 2,640 pi. So this is the radians over hours, over 1 hour. Cool. So multiply that by your R, your omega times R, right, is your linear speed, this V. So here we go, we're ready for it. V equals R omega, right? So that is 6.5 times 2,640 pi over O. And so this is meters, right? And this is over 1 hour. So let's multiply it. Oh, but wait, there's actually going to be one more thing we need to do, because we need it to be in kilometers per hour. But we can wait until the very last step in order to address that. So 6.5 times the 2,640 times pi, and we're just dividing by 1 hour, so there's actually no calculation associated with that. It's just a units thing. We're going to get that this is approximately, I'll do some squiggle equals, 53,909.72994 and it just kind of goes on forever. Oh, but wait, this is in meters, y'all. Meters. So in order to get it into kilometers, right, we need to move this decimal place over 1, 2, 3 spots to the left. So to convert to kilometers. So then your final answer, and we are going to round to the tenths place for no particular reason. They didn't specify what place value we would round to. This is just when I checked my answer in the back of the book, that's what they had done. So apparently that's the convention. How would you know that? I'm not sure. In the homework, they will always give you a decimal place to round to. So if I'm rounding to the nearest tenth of a kilometer, it'll be 53.9 kilometers per hour. Cool. Fun. Gravitron. Not that the gravitron would be fun. Gross. I would never write that right again. But this problem sure was fun, doing all that unit conversion. Love it. Okay, so we've had some fun looking at these trigonometric, or sorry, these radians and degrees and being able to go back and forth from them, and that's all of it going to be very well and good for this next bit. So we want to introduce trigonometric functions. These are your sine, your cosine, tangent, cosecant, secant, and cotangent. Those are all 6 of the trigonometric functions. And we want to do it using what we call the unit circle approach. Certainly there's something called triangle trig that I'm sure you guys have been familiarized with in your geometry days. And while it does come up here and there, I find it to be not super helpful to think about most problems in that way. I like this unit circle approach. And what you might see here on this screen right here is a really helpful representation of unit circle. You will notice that you just have a wealth of information here. It's a little bit color-coded, which is cool, and you're going to find lots of bits of symmetry and patterns. Anyway, you may be wondering, why are we learning this? What good is this information? Well, if you have any kind of application that talks about things moving in a circular path, for obvious reasons in the previous section, you can see how that might be advantageous to know how to work with a calculating device that has that shape to it. Also, if you have anything that is associated with wave-like patterns, well, the unit circle is able to exhibit things with wave-like patterns. Is this gonna actually, hold on, control click. Yeah, open it with Chrome. I don't know why I would even ask. So here is just a little bit of a beautiful representation of a sine wave and how its trajectory lends itself to the unit circle. Oh, isn't that gorgeous? So there's a hyperlink in there to that one. Cool. And then there's also way more complex applications that you can get into, where you get into sinusoidal waves meshed with other what's it called, types of functions. Did I not do this? Control and click, and it's not going to open it, or it will. It is opening it? No. Now you guys are saying where I got this from. Open hyperlink. I don't know. It's not going to show this. And control and click. I don't know why it's opening it, but this is getting into an exponential sinusoidal like combination function. It gets wild. Oh, there we go. Now it's doing it. It just had a little bit of a delay. All right, let's get this add. 1, 2, 1. There we go. So, wow, another add.
T, it becomes K, y of s.
Oh,
for b, y prime from the rule above.
And it just continued playing it.
This video was sponsored by Brilliant.
First.
Here we have a mass on a spring. If I
We
pull
don't
it,
even need to like listen to it. I just wanted to show you a visual in which we have, okay, he's talking about a mass on a spring and some dampening, right? So it's like either it could go back and forth in a very uniform way. It can be over damped, in which it just kind of like goes out and then never comes back in its in its movement. But then there's also where it could be slowing down It's a accordion-like movement, and that's where it's sinusoidal and exponential decay at the same time. Anyway, you'll get into that kind of stuff much later on in your mathematical careers. That's not something at all as what we're talking about. I just wanted to give you guys some kind of heads up context that seems fun. Okay, so yes, radians, degrees, both of these measurements are certainly in play, and we want to use them in order to find positions on unit circle. And so the positions are associated with the cosine, which is in the x position, and the sine, which is in the y position, associated with t. Now t is the distance from the initial starting point, which is always at 1, 0, and to some point on unit circle. Okay, which is also associated with arc length, right? Like those are pretty much the same thing. Now, also, t later on gets replaced with theta, which could be represented by either the radian version of the measure, or the degree version of the measure of the angle that's formed given the position on the unit circle associated with the terminal side of the angle formed. Okay, so this bit right here is something that we might want to reference later. So I'm going to go ahead and right now copy it, and anytime I want to use it later on, I'm just going to paste it directly into the notes. Okay, so there is so much going on here. There is so much information in this figure to quote-unquote memorize. The last thing I want you to do is to feel like you have to necessarily memorize it. But it is good information to internalize. What I would recommend that you do is try your best to find the patterns that are associated with this. So you can see that the division by 6, right? So the pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6, those 4 inputs and outputs associated with those positions on unit circle have a pattern to them, right? Don't they have the same numbers in your x and y positions, only different signage depending on what quadrant it's in? Yes, and you can use that to your advantage for both the pi over 4 multiples and the pi over 3 multiples. So please look for the patterns, and don't spend too much time trying to quote-unquote memorize outside of the quadrant 1 stuff. Quadrant 1 is where it's at, and it just kind of folds itself over in quadrants 2, 3, and 4. Okay? Also, there's these positions that are easy to remember and memorize, relatively speaking, and that's going to be on the axes themselves. Those positions are either zeros, ones, or negative ones, depending on, you know, what axis you're lying on and what part of the axis. Okay. Yes, so I say here, yes, notice the patterns, and then you will want to have your inputs and outputs. Whoops, I zoomed out a little bit. Associated with sines and cosines, irrespective of x and y. So your x is going to be your cosine of t or theta, as the case may be later defined, and then your y's are going to be associated with your sines. And then you have these other trigonometric functions, your tangent, which is the ratio of the sine and the cosine, and then you're going to have your reciprocal functions as well, which lend themselves to other applications that are going to be talked about later on. We're not going to focus on those as well. We're going to just introduce them, play around with them, and leave them at that for now. So for the first example, I want us to find the exact values of the 6 trigonometric functions of t given this position in unit circle. So you can just refer to unit circle, this figure right here, in order to answer this question. Okay, so I'm going to go ahead and plop unit circle down right here. See how gracefully this occurs. Does it do it? Yeah, it does it on top. That's great. Okay, and how I need reference it, I have it at my disposal, so there you go. So where's the ordered pair 1/2 negative 3 root 3 over 2? Well, let's see, scanning around. Well, hold on, if x is positive, then I have to either be in quadrant 1 or quadrant 4, right? Right. And look, 1/2 with a negative root 3 over 2, that is associated with this point right here. Okay, so you know what? And we don't even need the degree measurements at all. We just know that what the sine, actually we do not need unit circle at all for this one. I don't even know why I put it in there. We just need to know that, oops, excuse me, let's get rid of that and get the right utensil out. The sine of t, because we're talking t here, we're not talking theta just yet, and t again was the distance from the starting point to this position, this ordered pairs position on unit circle. So the sine of t, therefore, is going to be this little bit right here, this negative root 3 over 2, or the y of your ordered pair. The cosine of t is going to be the x of your ordered pair. The tangent of t is going to be the ratio of y over x, which is the negative root 3 over 2 over 1/2, which the 2's are going to cancel out here. If you're familiar with doing the simplification without having to rewrite it, and you're going to get negative root 3 for the tangent of t, and then you have your reciprocal functions, okay? So, and they are cosecant t, secant t, and cotangent t, respectively. So I like putting them in this order and right next to, like in line with these original trigonometric functions, so that I just go ahead and take advantage of the reciprocal nature, because the cosecant of t, you might notice, is the reciprocal of whatever you had for y, right? Okay, so, and the secant is the reciprocal of x, and the cotangent is the reciprocal of the tangent. So it's just x over y, rather than for tangent of t, it was y over x. So just flip them over. But if you ever have a radical in the denominator, when you flip it over, you're going to have to do the, what do you call it, rationalizing the denominator, right? Like this kind of a thing. And eventually you're going to rationalize the denominator, and your final answer here will be negative 2 root 3 over 3. We could talk about the details of this if you'd like. Now, secant t is going to be the reciprocal of 1/2, aka 2 over 1, or just call it 2. And the cotangent is going to be the reciprocal of negative square root 3, which is negative root 3 over 3. Again, how am I doing that so quickly? Well, I know how to rationalize denominators relatively quickly. So here they all are. And this is associated with this. Here I'm just going to connect the final answers there. And then for that and that. Okay, that's all 6 trigonometric functions. And even though I erroneously referenced the unit circle, it was so unnecessary actually. You just need to recognize that this first thing is your cosine of t, and the first part of the ordered pair, and the second item in the ordered pair is your sine of t. You do that and you've got it. You've got everything that you need for that. All right. Moving on. Now it behooves us to relate this distance on the outer edge of the circle t, as it's been defined, to theta. Now that outer edge of the circle distance t is the arc length, the way that we were referring to it earlier, right? S. So this is, so just recall that this is your arc length. And what was the relationship between arc length and radians, the radian measure theta? Well, that radian measure theta was that many radians, basically. So yeah, so as long as the radius was equal to the arc length there, then the radian was just that many radians. So hopefully that all can make sense for us, and we're just going to recognize that t is equivalent to theta. Theta is going to be t radians in measure. Okay, and again, remember, if you have a downward swing, like that distance is the result of a downward swing, then that just means that your theta is negative. Okay, great. So then we just have a quick development of the six trigonometric functions in terms of t radians. Now we're going to think about them in terms of theta, which could either be measured in radians or degrees. Okay, so here is a quick breakdown of some of the more famous positions on unit circle, like for instance zero radians as being associated with 0 degrees as well. It's all 0, 0, 0 all the way through. And so the position on unit circle, when you traveled no distance, there's absolutely no swing whatsoever in your scenario, then the cosine of it, the x position, is going to be at 1, right? Because remember, we're talking unit circle, so the radius is 1. So that means the distance from the center to that outer edge is going to be exactly a 1. And it's a straight line distance, so the cosine is a 1. Now the sine is associated with the y value, and what's the y value of that position, that point's position? Well, it's 0, so that means that the sine of 0 radians or 0 degrees is 0, y equals 0. Now the tangent is going to be the ratio of the sine over the cosine, so that'll be like a 0 over a 1, right? And then the secant is going to be, 0 degrees, which will be the reciprocal of 1, which is 1 over 1, so that's a 1. Since the y coordinate is 0, that means that the cosecant and the cotangent of 0 radians or 0 degrees are therefore undefined. Moving on to some other famous ones in figure 21, B, C, and D, we have all of the inputs and outputs, the 6 trigonometric functions described at the ordered pair 0, 1. So 0, 1 is associated with a 90-degree angle. It's a 90-degree swing, or pi over 2 radians. And so the positioning there for your sine, which is associated with your y, will be a 1, and the cosine in that for that radian or degree measurement of pi over 2 or 90 degrees respectively will be a 0. So take into account which ones of the 6 trigonometric functions will be undefined. It'll be your tangent, in which you have, an x in the denominator space for both of those, equaling 0. So therefore the tangent and the secant are undefined. But the cosecant is defined, and it occurs at the reciprocal of that y output of 1, so 1 over 1 is just a 1. And then the cotangent, which is the x over y, that'll be a 0 over 1, or just a 0. Okay. Moving on to 180 degrees swing of the theta, or it'll be a pi radians. What are the 6 trigonometric functions there? Well, here they all are in their entirety. This time the y is 0 again, but this time, and then the x is a negative 1. So put all of the numbers in the correct positions, and again recognize that cosecant and cotangent will be undefined there. And then lastly, for 270 degrees, 3 pi over 2 radians, that's a 3/4 of the way around swing of your angle there, if it's a positive angle, that is. And your corresponding trigonometric functions will have those following outputs. And then here is a pretty non-exhaustive list of useful radians and degrees and their corresponding sine, cosine, tangent, cosecant, secant, and cotangent values. It's just all of the information that was just outlined in figure 21, parts A through D, but in a table, just all in one place. Quadrantal angles is what it's called. So those are basically your angles in which the terminal side is going to be on some axis. Okay, and furthermore, you could swing around this unit circle more than 2 pi times, or 360 degrees, as we kind of alluded to in the previous section. So in that case, you're going to just determine where the terminal side of the angle lies after all the swings are done, and then you're going to find that there are equivalences that occur here, or maybe in some of the other angles that are presented in the unit circle. And if not, then you're going to have to rely on your calculator for some calculations. So here in this next figure is kind of where I allude to that, and then we're going to start getting into some examples here. Okay, so as you can see in figure 22 part A, we are trying to figure out where a theta of 3 pi rests in terms of the terminal side is concerned. So notice that 3 pi is a multiple of pi, sure, okay, but when you go around the circle 2 pi times, you end up right here, and then you have one more pi of rotation to go. So from here, go one more pi's distance, and then here is where 3 pi rests in terms of the terminal side. So that means that 3 pi, as far as angle measure is concerned, is equivalent to just simply pi. Any multiples of 2 pi are just literally spinning the wheel, okay? Spinning a wheel, a full revolution is 2 pi, and then anything after that in terms of radian measurements is going to give you the location of the terminal side. And furthermore, if you have a negative degrees or radians, just remember that you're swinging not counterclockwise like you would do for a positive angle measure, but you're going to swing swing clockwise, not counterclockwise, rather. Okay, so hopefully I said that somewhat correctly the first time. If not, what I meant to say is positive angles equate to a counterclockwise swing, whereas negative angles are a clockwise swing, just to make it confusing. Okay, so and this one is in degrees, so certainly we'll go back and forth between the different types of measure for our angles. Okay, here is where the examples start. So let's find the exact value of the cosine of 7 pi. Okay, so here we go. Let me find my note page there. Here we go. So cosine of 7 pi. Well, notice that 7 pi can be rewritten as some multiple of 2 pi. So if I want to separate a multiple of 2 pi, so what's the largest even multiple of pi? Well, that would be 6 pi, right? And I could separate that out and say that that's what's going on inside of the argument of this cosine is still equivalent to 7 pi, right? But this right here represents 3 full revolutions, which after I've exhausted the 3 spins around the unit, I'm going to end up at my same initial position again. So really, it's equivalent to just having the cosine of pi. And what is the cosine of pi, you may be wondering? Well, you can, if you want to. Let's see, do I have unit circle at my disposal? Sure I do. Okay, we'll just go ahead and pop unit circle in here. See if it's a good reference for me. And yes, what is the cosine of pi? Well, pi, as a radian, is right over here, and the cosine is the exposition, so that'll be a value of -1. So therefore, the cosine of 7 pi is equal to -1. And along the way, I recognize that through my work that it's equivalent to the cosine of just pi. Okay? Now, cool. So now let's go ahead and up the ante on the difficulty level and talk about the secant of 8 pi. But wait, it's actually not that crazy, because 8 pi is just 4 full revolutions around unit circle. So this is going to be equivalent to secant at the starting position, 0 radians, right? And what is the secant of 0? Well, the secant is 1 over the cosine of 0. which will be, what's the cosine of 0, y'all? Well, the cosine of 0 is going to be 1, because here I am at the 0 position, right? And the cosine is always the thing in the x position of the ordered pair. So that'll be like a 1 over 1, but just call it a 1. So therefore, the secant of 8 pi is equal to 1. All right. Now let's have an expression, but let there be some extra, stuff in there, an operation, some multipliers, and let's have the angle measurement in degrees. Okay, so we could still use this unit circle figure here, and we're just going to be not looking at the radian measurements, which are closer to the outer edge of the unit circle, but the closer to the origin measures are in degrees. Okay, and again, we're saying do not use a calculator. Great. So let's figure out what is the equivalent of the cosine of 90 degrees. Well, that'll be the same as the cosine of pi over 2. Or, I mean, we could just go here. Here's 90 degrees, pi over 2. The cosine is 0, okay? So this value is a 0, so it's like 5 times a 0. That's going to just zero out this entire term. Really, we could just kind of cross it out. And then we still have to subtract from 0 8 times, well, what's the sine of 270 degrees? Well, where's 270 degrees? Well, it's right here. That's going to be the sine of it is going to be in this the y position, right? So that'll be a -1 factor that we multiply here. So therefore, this expression settles down to -8 times -1, which is a +8. No calculator needed. We just need to get to know this unit circle. Okay, cool. So I'm just going to leave that there. And if I need another one, I'll just go ahead and grab it. Okay. So now we get a little bit more in depth on the unit circle material in the textbook, and I thought I'd just go ahead and present table 3 at this point, where they have all of the harder to remember values inside of unit circles. So not the quadrantal ones, but the ones inside of each quadrant. Yeah, those are the harder ones to memorize. But here they are in a table. If that's helpful to you, if that's more helpful than looking at the unit circle, which by the way, I'm going to go ahead and paste right here again so I can reference it, then by all means use the table. But I'm going to go ahead and have it there in order to find the exact value of this expression right here. So this cosecant of pi over 3, oh my goodness, well, I'm going to have to think about this a little bit further. Let me actually rewrite this. Oops. Use the right utensil, as 3 times, well, what is the cosecant? Well, that is 1 over the sine, right, of pi over 3. 1 over sine pi over 3. Plus, the cotangent is the, the cosine over the sine of pi over 4. Okay, great. So now I can go to my unit circle reference if I haven't memorized it yet, and kind of, for more or less, just plug and chug. So what is sine of pi over 3? Let's start there. Well, pi over 3 is here. Sine is the number in the first position, which is, in the second position. My bad. I said that sine was in the first position in the order pair. My bad. That was not the right thing to say. The sine is, of course, in the second position, or the y position. That'll be the root 3 over 2. So I have 1 over root 3 over 2. So I'll have to do a little flippity-doo-dah there. Nothing I can't handle, though. And then over here, let's look at the pi over 4 position. Now that's right here. Oh, cute. I love pi over 4. You know why I love pi over 4? Because the sine and the cosine are the same value. So I can tell that I'm going to have basically something that just goes to 1. So without even writing this right here, the cosine over the sine, or the sine over the cosine. So the cotangent and the tangent, therefore, at pi over 4 is actually 1 no matter what. Isn't that fun and cute? And a cool thing to recognize. So that'll just be a 1. I'll go ahead and put that in straight away. And I'll say because sine of pi over 4 equals cosine pi over 4. Okay, great. So a little bit of a parenthetical note there. Great. Now let's do a little bit of algebra on this biz. And just recognize that that is going to... so really, I flipped this over. 2 over root 3, but wait, I gotta rationalize the denominator. That'll be a root 3 and another root 3. These 2 root 3's cancel out with this 3 on the outer edge right there, and that'll be a 2 root 3, and then I still have to add 1 to it. So my final answer will be 2 root 3's plus 1. Now this 2 root 3 term is an irrational term, so you should not try and combine it with the 1 that's on the outskirts there. Okay, great. We are almost finished there. Well, no, we've got, LOL, we have 3 more examples to tackle. So we do still have a little bit of practice left ahead. Okay, stick with me here, folks. Let's find the exact values of all 6 trigonometric functions for these 2 different angle measures. One of them, of course, is in radians here with number 54, and then another one in degrees. And furthermore, the degree measurement is negative, so it's extra fun. Okay, referencing a unit circle might behoove us here, so I'm going to give myself another iteration of that while I go. Put that off to the side while I work on both of these problems. And here we have it. First of all, 13 pi over 6, that seems like it's a little bit more than pi over 2 in value, right? Pi over 2 being an entire revolution around this unit circle. Am I correct, right? 0 degrees, it's also equal to pi over 2, which is not stated over here, but it's totally true. Or sorry, 2 pi rather. This is 2 pi as well. You'll want to see if you can kind of, what's the word I'm looking for? Break this up into pieces. Like for instance, can I rewrite this as some form of pi over 2, or sorry, some form of 2 pi, and then separate it from some leftover bits? Sure enough, I can. Notice that this is equal to 12 pi over 6 plus pi over 6. You feel me on that? Now, how did I know to separate it this way? Experience, I guess. I'm not really sure how to explain it other than that. You want to see if you can separate out as many 2 pi's as you possibly can, because this, as you'll notice, that is reduces itself to a 2 pi, which is 1 full revolution, right? So this is the same as, you know, starting again at the beginning position, and then you have this leftover bit waiting in the wings. So that means that this 13 pi over 6 is equivalent to just a pi over 6. So now let's talk about the 6 trigonometric functions. Sine of 13 pi over 6, cosine of 13 pi over 6, tangent 13 pi over 6. So we're going to find all those values. We're going to find their reciprocals, which is kind of running out of room here. Let me see. I can move this over just a scotch more. Sure. And then we'll have the other ones right here. So cosecant, 13 pi over 6. Oh, pi goes here, 6 goes down below. Gosh, I'm tired. Okay, we'll get through this, guys, promise. Secant, 13 pi over 6. And then cotangent, 13 pi over 6. Let's I'm just gonna be writing, unfortunately, on top of my unit circle. Okay, now remember, it's equivalent to pi over 6. Where's pi over 6? Here it is. Pi over 6 is the same as 30 degrees, which is the same as 13 pi's over 6. So here's 12 pi over 6 is this first, one whole revolution, and then the 13th pi over 6 is right here. This is where it lands, and so this is equivalent to the 13 pi over 6 is just this pi over 6. So what is its cosine? We could start there. That's the root 3 over 2. Root 3 over 2. The sine is the 1/2. The tangent is root 3 over 3. 3 over 3. The cosecant is 2, right? The reciprocal of the sine. The secant is 2 root 3's over 3. 2 root 3 over 3. And the cotangent is a root 3. Sorry for writing on top of the unit circle there. Kind of not helpful. But I am going to move it downward for this next calculation. So hopefully we can still reference it relatively clearly despite all of the markings that we made. Okay. Sorry, let's go ahead and erase this little guy. And get rid of you. Great. We know that 0 degrees is, 0 radians is the same as 2 pi radians. But we're not talking about radians for this next one. We're talking about degrees, and 240 of them, and it's a negative swing. Okay, first let's talk about what it looks like to be 240 degrees positive, okay? And we'll do this in the celestial print thing. So 240 degrees looks like, oh, whoops, I went past it. LOL. Let's try that again. 240 degrees is right here. So here is me heading and stopping at 240 degrees in the positive sense. So the positive 240 degrees looks like this. So a negative 240 degrees will be the same amount of swing but in the opposite direction. So we should end up at the mirrored reflection over the x-axis in regard to that. So this is a theta equals 240 degrees. And then here is negative 240 degrees, ends up right here, okay? Negative 240 degrees is therefore equivalent to a positive 120 degrees, okay? So take that into account here. So that means the sine, oh, I meant to do this one. Let's erase it. Sine of negative 240 degrees, cosine 240, tangent negative 240, cosecant negative 240, secant negative 240, and cotangent. And I assigned all of my 6 trigonometric functions in this relative position to one another because I feel like it's most helpful to do them quickly. So the sine and the cosine are on, like, as long as you find the equivalent position, it's on unit circle itself, right? So that'll be root 3 over 2 for the sine, negative 1/2 for the cosine, negative root 3 for the tangent, which is the sine over cosine. Okay, so you got to do the math there. And then the cosecant will be 2 root 3's over 3, which is the reciprocal of this this mess right here. And then here it'll be negative 2 for the secant, which is the reciprocal of negative 1/2. And then finally the cotangent will be negative root 3 over 3. Cool, 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 cool. So that's all that is. Okay, it looks like we have one more example we're going to tackle, and then I will turn you loose on your own endeavors, and then we'll also be ready to talk about it in class. What do you do when you have to work with something that's not a unit circle? Can you still use all of this information? Sure enough, you can. You just really have to throw in this factor of r, which is whatever the radius is of your circle that doesn't have a radius of length 1. Like your circle in this case is going to have a radius of some other length. And so you can see in the figure 32 visual, we have concentric circles in which the inner circle is the unit circle, and then the outer circle is the circle of some unknown radius r, which technically is something bigger than 1, although you could have the radius be less than 1 and this would still absolutely work. So you'll just need to make the following adjustments that you see in this yellow box, aided by what's given here in this little blurb over here, okay? This series of proportions. Okay, so let's go ahead and take into account these adjustments to the 6 trigonometric ratios in order to find the exact value of the 6 trigonometric ratios of theta in this very specific situation where we have 5, -12 being the point on a terminal side of angle theta. So we're not dealing with unit circle anymore. We're dealing with some other type of a circle with a particular radius. Now, the first thing you'll want to do is take your x and your y, and you will want to x equals 5, y equals -12, and you want to feed them into this circle formula in order to calculate your r, okay? So x equals 5, so that means 5 goes there, y equals -12, it goes in the y position, and you're going to use that to calculate your r's. You're going to have to square root it. So here we have 25, here we have 144. Very much awesomely, they sum to a perfect square number. And remember, you're talking about a distance, r, so you're just going to take the principal square root, which is going to be, thank God, a whole number of 13. So here r equals 13. Okay, so r is 13, and your x and your y's are there. So go ahead and take that into consideration to find all 6 trigonometric ratios, which you see presented here in this yellow box. So it's just as easy as plug and chug after that. And we have the following. So, and again, just to be clear, as far as the visual is concerned, everything we've been doing, working up until this point for section 5.2 work has been a unit circle, a circle centered at the origin with a radius of 1. In this scenario, with number 78, we are working with a circle still centered at the origin, but its radius is 13, so it's like, it's quite a bit bigger. Anywho, let's go ahead and punch out these 6 trigonometric ratios, and then we will be on our way. Sorry, it's not sine of x, it's sine of theta. Theta is unknown to us. We don't care what it is. We just want the output of these 6 trigonometric ratios here. And it'll be relatively easy. We've done all of the hard work. Okay, so the sine of theta, you will recall, is y over r. So that'll be -12 over 13. And cosine of theta is x over r, which is 5 over 13. And then y over x is going to be your tangent theta, -12 over 5. And then take the reciprocal. Like the last 3 trigonometric functions, the reciprocal ones, couldn't be easier to calculate, because just flip them over, right? So that'll be 13 over 5, and then -5 over 12 for the last one. Phew! Okay, what a wild ride. I'm sure you guys have lots of questions. There's definitely more details that I could have covered here, but I just need to cut the lecture off at some point. Let's have a rousing discussion in class. I can't wait. See you then.